Welcome to Covalent Bond Energies and Chemical Reactions. Alright, so it's important to note that the energy required to break a bond is dependent upon the molecular environment. So exactly how much energy is involved to break the bond depends on what exactly is bonded to the atoms in question. And this means that if we look at something like the stepwise decomposition of methane, every time we pull a hydrogen atom off, so we go from CH4 to CH3 plus hydrogen atom, and then CH3 to CH2 plus hydrogen atom, and so on, down to atomic carbon and hydrogen, we have to put in some energy. Well, the first time we pull a hydrogen off, we have to put in 435 kilojoules per mole. Well, the next time we put in 453 kilojoules per mole. The next time we put in 425, and the last time we put in 339 kilojoules per mole. So the total in pulling off all four of them is 1652. I discussed this in the last video, but it's different for each hydrogen that we're pulling off. So this 1652 divided by 4, 413, that's an average for pulling off these four. But none of those four is actually 413 kilojoules per mole of energy to take off. So we use this average 413 kilojoules per mole of energy as the energy associated with the carbon-hydrogen bond, but it's really just an average. And again, it depends on what else is bonded to the carbon and hydrogen. So here we have some measured carbon-hydrogen bond energies for different molecules. So when we have 1 hydrogen and 3 bromine atoms bonded to the carbon, that carbon-hydrogen bond energy is 380. When we replace the bromines with chlorines, it's still 380. When we replace them with fluorines, we now have a bond energy of 430. If we have 2 carbon atoms bonded together and 3 hydrogen atoms on each of the carbons, that bond energy is 410. And so our carbon-hydrogen bond energy depends on what other atoms that carbon atom is bonded to. It would depend on what else the hydrogen is bonded to, but hydrogen will only form one bond. So thus far we've only discussed bonds in which 2 electrons have been shared, so single bonds. But if 4 electrons are shared, then the 2 atoms are bonded together with a double bond. And if 6 electrons are shared, then we form a triple bond. So 2 electrons form a bond. So for every additional bond that we want to add, we need to share another 2 electrons. So the bond energies of multiple bonds are larger than for those of single bonds. So multiple bonds are stronger than single bonds. And a triple bond is stronger than a double bond is stronger than a single bond. So as the bond strength increases, the bond length decreases, because as that bond gets stronger, they're pulling those 2 nuclei closer and closer together because it's pulling stronger. The stronger that pull is, the closer together those 2 nuclei are going to be before that repulsion between the nuclei stops that attractive force. So bond energy values can be used to approximate energies for reactions. So if we look at, say, the formation of hydrogen fluoride from its component elements, this process involves breaking 1 hydrogen-hydrogen bond and breaking 1 fluorine-fluorine bond, and then forming 2 hydrogen-fluorine bonds. So breaking the bonds requires energy to be added. This is a positive delta E. Forming bonds releases energy, so a negative delta E. This is something that you need to be aware of all the time in chemistry. Whenever you form bonds, you get energy out. When you break bonds, you have to put energy in. So this means that we can write the energy change for a chemical reaction as follows. So the energy change for the reaction is equal to the sum of the energies required to break the old bonds, so the positive signs, plus the sum of the energies required released in the formation of the new bonds, so negative signs. And we can write this mathematically as the delta E for the reaction, so the change in energy of the reaction is equal to the sum of the number of bonds of each type broken times the energy change for that, for breaking that bond, minus the sum of the number of each bond of each type broken times, or rather, the number of each bond of each type formed times the energy change formed. So N there is the number of moles of a bond that is broken or formed, and D is the bond energy of the bond that is broken or formed. So if we look at the formation of 2 moles of HF, hydrogen fluoride, we have a case like this. We have the bond energy of the hydrogen-hydrogen bond plus the bond energy of the fluorine-fluorine bond, because we're breaking those. It's 1 times each of those, minus 2 times the bond energy of the HF bond. So we have 1 mole of hydrogen. Well, that gives times the bond energy for hydrogen, 432 kilojoules per mole of hydrogen, plus 1 mole of fluorine times the bond energy there, 154 kilojoules per mole of fluorine, minus 2 moles of hydrogen fluoride times 565 kilojoules per mole of hydrogen fluoride. That gives us minus 544 kilojoules. So we should get out 544 kilojoules of energy if we create 2 moles of hydrogen fluoride. So that was covalent bond energies and chemical reactions.